So the final subunit of the topic around transition metals and periodicity is that of the colored complexes associated with this first row of the transition metals and how it comes about. So in this unit we'll be looking at the way that the D sublevel splits, why complex D block elements are colored, or the complexes of them anyway, and this is related to art in the sense around complementary colors, and explain, depending on the identity of the metal ion, the oxidation number, and the ligand, what the color of the transition metal ion complex will actually be. And this will be linked to explaining the effect of different ligands on the splitting of these d orbitals. So essentially it comes down to a theory, this prediction of color, called crystal field theory. Okay, so in crystal field theory, basically it suggests that the different orbitals behave differently when they get ligands interacting with them. Okay, so you might remember from the electron configuration that the d orbitals come in 5 different forms. The dxy, the dyz, and dxz, depending on their direction in 3 dimensions, which are of a lower energy state, therefore more stable, and the dx squared minus y squared and dz square orbitals, which are of high level, which means that when electrons enter them, that means that they have a split d sublevel. Okay, so the x, y, z axes are where the atomic axis is where the ligands actually are joining, okay, which you can see here, these x, y, and z axes. This is where the ligands actually join to the orbitals. So the ligands, which we discussed in the last subunit, actually decide decide the energy of these sublevels. Okay, so strong field ligands, which we'll discuss soon, cause a split between the low energy levels and the high energy levels. Okay, because what happens is in higher energy levels, the electrons of the ligands are actually repelling the electrons in the metal, which of course causes a high energy situation. Okay, remembering of course that only happens in the electrons of the ligands are on the same axes as the electrons in the middle. Okay, or in the metal. So you see this in terms of crystal field theory, okay, in terms of the energy splitting. Okay, so you've got a free electron pair from the ligands, and obviously the electrons are attracted to the nucleus of the metal cation because it's nice and positive. Okay, but the overlapping orbitals in terms of the higher energy dx squared and y squared and dz squared orbitals can cause the electrons to move to the split lower energy orbitals dxy, dyz, and dxz because they're more stable. And the reason for the stability is there's no direct overlap with the ligand, so it's actually reducing the repulsion between the ligand and the orbitals of the metal cation. And this difference in energy is known as delta naught, or the crystal field splitting energy. And it depends on 3 different things. It depends on the size of the metal cation in the middle, okay, and this is related to the movement of electrons between the split d orbitals, okay, and this will relate to different wavelengths being absorbed and also emitted by the complexes. And we'll see this as the myriad different colors of particularly transmetal ion complexes. Okay, so this crystal field splitting energy depends on 3 factors, which I'm now going to go through. The first one is the ligand strength. Okay, so more negative charge density of ammonia makes this splitting greater than you would see in water. As you can see from the animation, there's more negative charge on the nitrogen of ammonia than there is on the oxygen of water. Also with fluorine, which has a larger electron density, than chlorine, so the splitting again increases. Okay, which again you can see by the animation here comparing HF. Looking at HF, large negative density. The size of the metal ion also determines on the size of the splitting. Okay, so as you go down a group, then the splitting energy or difference in splitting energy increases due to more orbital overlap. Okay, because it's getting larger and larger, of course. And it's also based around oxidation state. The higher the oxidation state of the cation, the more the splitting increases due to the greater attraction of the nucleus to the ligand and hence more orbital overlap, okay, because it's a larger charge. Those electrons on the donor ligand are being more attracted to the positive cation in the center. Okay, you can see this by the diagram here. Cobalt, the 2+ and 3+ ions of cobalt, you can see that there is more potential for orbital overlap due to the larger charge on the associated cation in the center. So this crystal field splitting energy is basically the difference between the lower energy dxy, dyz, and dxz suborbitals and the associated higher energy dx squared minus y squared and dz squared suborbitals. Okay, so it's this difference between these two, which we've looked at the reasons why this split occurs and the difference and how we can increase or decrease this split. So the ligands are important in determining the difference in field strength. The strength of a ligand determines the amount of the splitting. So splitting can be spin-free or spin-paired. So spin-free basically means that in the complex, the transition metal electrons favor being unpaired in the suborbitals. Whereas spin-paired, they are favored to be paired up in the suborbitals because that is the most electronically favorable. And the reason why that occurs is if there is a high energy split between the low energy suborbitals and the high energy d suborbitals. Okay, so here we have the example where there is a high energy split. Okay, so you get a low spin because the majority of them end up paired up. Whereas if there is a low energy difference between the high energy and low energy suborbitals, then you're going to get high spin, where there is going to be a lot more of the electrons are going to be unpaired in the suborbitals. So this can actually change the properties of the complexes. So remember in the previous unit we discussed diamagnetism and paramagnetism. Okay, so paramagnetism or magnetism occurs when you have unpaired electrons. So cyanide is a very strong field ligand and it creates diamagnetism in the complexes. And water is a weak field ligand creating paramagnetism. So if you look at manganese, what would that be? That would be manganese 6, so 6 minus, so manganese 5+. The complex with cyanide is diamagnetic because all the electrons want to pair up in the lower energy suborbitals rather than move up into the higher energy suborbitals because of the large splitting due to the strong field ligand that is cyanide. Whereas for something like chromium in solution, chromium 2+ in solution, then it's going to favor being paramagnetic because the energy difference, okay, of the split, because the splitting is quite low, is not very high between the higher energy suborbitals and the lower energy suborbitals. So the electrons will tend to favor going into unpaired suborbitals. And so it's going to be paramagnetic. So looking again at electron configurations, the lower energy state is usually written as T2G, and the higher energy state is written as EG. So the configurations are written as follows. Okay, so for this one, when you've got a high crystal field, okay, a high splitting, then it's going to be T52G and E0G, because all of the electrons are going to be in the lower energy degenerate, the lower energy suborbitals, whereas if you have a ligand which doesn't induce this large crystal field splitting, then the electrons are going to be able to move up into the high energy suborbitals. So in this particular case, it'll be T4G and E2G, okay, because the electrons can jump because they've got it's a lower energy field.
Describe the effect of different ligands on the splitting of d orbitals. Well, I'm going to start by drawing out just the electron configuration for copper. So argon, 4s1, 3d10. Remember, that's one of those weird ones. Copper and chromium are the weird ones. Putting in arrows to represent the electrons, following Aufbau, Hund and Pauli rules. Now I need to make it into an ion, because complexes need ions, at least in this part of the syllabus. So I've knocked off the electron from the fourth shell, the valence shell, to make a copper 1+ ion. Water is behaving like ligands. It has a lone pair of electrons capable of making a dative covalent bond with a central transition metal ion or atom, and I've coloured those in purple. Now those ligands, those water molecules, cause the d orbital to split. The ligands cause the metal ion d block orbitals to split. It's a 3-2 split. If I was to shine light through it, actually in this case nothing happens. For a colour to be seen, you need a partially filled d orbital, and this d orbital is completely full. There is no room for an electron to be promoted from the lower to the higher. Well, what does that matter? Well, we'll find out in a second. But a partially filled d orbital is what we need if we're going to have a coloured complex. So what colour is no colour then? Well, colourless, or you could say no colour, or white. Sometimes confusingly black, but we'll stick with no colour or white. Let's reset this little experiment. And there's copper again. I'm going to make it copper 2+, putting off a couple of electrons there. Now I have a partially filled d orbital. And that's going to give me coloured complexes. So I'm going to bring the water ligands in again. Now I could use ammonia, I could use hydroxide, chloride, cyanide. All of these are different ligands that will split the d orbitals in different ways and give different colours. Again, in purple, purplish pink, is the dative covalent bonds. The d orbital split, it's a 3-2 split. And now when I put light through, some of the light's disappeared. So this is going to look blue. I shone all the colours in at the beginning, red, orange, yellow, green, blue, indigo, violet, and only a few colours came out, the bluey colours came out. So this will appear blue. So what happened to that energy? Well, it shakes those electrons around, and one of them may be promoted from the lower to a higher energy level, and that took energy, and that was the energy of that light. So that's what happened to the light. It was removed by the action of putting an electron up to a higher energy level. Now we might ask you what colours. We'll tell you what colours absorbed, and you have to tell us what colour the compound is, or vice versa. So here's the trick. Roy G. Biv, put them in a circle, all the colours. I don't have blue, indigo and violet on my active board, so I put B, I and V. If orange is absorbed, then your compound will appear kind of bluish. It's opposite. If green's absorbed, then my compound will appear kind of violety reddish. So whatever colour's absorbed, look across the colour wheel to see the other colour. It's called the complementary colour, and that's the colour of your complex.
So yeah, the choice of ligand determines what color the complex will be. And in your data booklet, you have something called the spectrochemical series, which shows the splitting strength of a group of ligands. Okay, we have the weak field ligands like iodide and bromide, and the strong field ligands like cyanide and carbon monoxide and ammonia. So weak field ligands cause spin-free splitting, and strong field ligands caused spin-paired splitting. Okay, because basically spin-paired splitting occurs because you've got you make the delta naught so large that it's not energetically favorable for the electrons to move up into those high energy suborbitals, whereas weak field ligands mean that the crystal field is the difference is small, the split is small, so it's energetically favorable for electrons to move up into those high energy orbitals. So this explains the square planar arrangement for, say, copper 2+, Da configurations, with strong field ligands like cyanide. Okay, so what will happen is you'll end up causing a split like this. Okay, so you've got your large delta naught, okay, large crystal field split, but all these guys are now bunched up, so you can have the unpaired low spin variety of addition of the electrons, because with the greater repulsion of the lower energy orbitals, the ligands will best line up with the x and y axes of the dx squared y squared configuration. Okay, this guy here, the square planar configuration. This will allow them to be as far apart from each other as possible, rather than the dz squared configuration, which would be your tetrahedral arrangement, because you want to reduce the repulsion between the ligands, and also the repulsion between the d orbitals. Okay, this is why you get this formation here, the low spin variety. So in terms of other configurations, linear is z squared, because it's going to get slightly closer to the nucleus. You've got square planar with D8, which we've already looked at, copper 2+. Tetrahedral, as visually looks like the easiest access to the nucleus with a 3D model though, and octahedral, only symmetrical place for 6 ligands. Okay, so if you have 6 ligands, you have to be octahedral because there's no other possible symmetrical formation that you can actually form. Okay, and these are the splittings here anyway. Okay, so it doesn't make a difference if it's delta naught is high or low. With 6 ligands, you're always going to end up with 6 octahedral configuration.
Made possible with help from Eunice. A better world. Shouldn't that be a capital A? 13.2. What affects the colour of a complex? Well, there are 4 reasons, but the IB needs you to know 3 reasons. The first reason is the identity of the metal ion. Is it chromium? Is it copper? Etc. 2. The identity of the ligands. Is it water, ammonia, cyanide? And 3. Oxidation state of the metal ion. Is it +2, +3? Alright, so a complex is made of essential transition metal ion with ligands datively covalently attached. Now the 4th reason that isn't IB is how many ligands are attached, but we are only going to look at 6 ligands, the so-called octahedral shape. So the electronic configuration, shorthand, is argon, 3D, well I don't know, let's say 3D2. So when the ligands make their dative covalent bonds, the d orbital is going to split in a 3-2 fashion, just like that. And that is called delta E, the energy difference between the lower and the upper d orbitals. Light goes through, light is absorbed, and that energy takes an electron from a lower to a higher energy level. And what's left behind? Well, that's the colours that you see. So big split means a big jump, means big energy absorbed. Big energy being violet. So let's just reset this complex. If I have a small delta E, small split, small jump, small energy absorbed, so that's going to absorb red light to promote the electron. And as the split gets bigger, the light that's absorbed is going to have increasing energy all the way through to violet. So let's look at reason 1, the identity of the metal ion. Well, both of these have a metal ion that are isoelectronic to each other. They have the same number of electrons in the same place. They are both argon 3d5. So the manganese has 25 protons, and the iron has 26 protons. And so the more protons there are, the more interaction there is with the ligands, and the bigger the split. So manganese is going to have the smaller split, and iron, with one more proton, is going to have a bigger split. So how can we work out what colour is going to be absorbed? Well, I'm going to tell you that manganese absorbs green light. And so iron, if it's got a bigger split, it has to absorb a higher energy light, and it actually absorbs blue light. So looking at the manganese, green is absorbed. So what happens to that energy? Well, it's used to promote an electron from a lower to a higher energy level. Does it really matter which one and where it goes in IB? Now what's the colour opposite green? It's red, and so that's why manganese is a kind of pale red colour. That's the colour that's left behind. You've got to use the colour wheel. Iron absorbs blue light to promote an electron to a higher energy level. And so what colour is going to be seen? Well, what colour is opposite blue? It's kind of orange. Well, it's not quite that orange. So to be honest, the colour that's absorbed is kind of bluey violet. And so that's why the colours opposite are orangey yellow. So that's iron hexahydrate 3+ is orangey yellow. Let's look at another example. Both of these again are isoelectronic, so you have to be able to spot those examples. Which is going to split the most? Well, titanium has 22 protons and vanadium has 23. So titanium splits less than vanadium. An electron's promoted, and yellow light is absorbed with the titanium, and for the vanadium complex it must be higher energy, and it's actually kind of yellowy green light that's absorbed there. It's a higher energy, bigger split, more protons. The opposite of yellow is that kind of violet colour, so that explains the violet colour of the titanium complex, and the opposite of yellowy green is kind of violety red, which explains the colour of the vanadium complex. On to the second one, the identity of the ligands. Well, there's the spectrochemical series at the top. It's in the data booklet. The further to the right, the bigger the split for the ligands, and the further to the left, the lower the split. So let's look at this copper complex. First with water, and then a bunch of the water is replaced by ammonia. That's the first split. That's going to be the smallest split, because as you add ammonia, ammonia is further to the right on the spectrochemical series, the split's going to get bigger and bigger and bigger, and absorb higher and higher energy light. There's my colour wheel. The first one there is a light blue colour. So what sort of light was absorbed? Well, if it's a light blue colour, then it must have absorbed orange light, because that's opposite on the colour wheel. And as we go down, more and more ammonia is replacing the water ligands, so the split's going to be bigger. And so it's deep violet, right down at the bottom one, is the colour. So what was absorbed to make it look deep violet, well, that has to be yellow. It has to be a higher energy light than orange. because it's a bigger split. Yellow is higher energy than orange. And the third reason is the oxidation state of the metal ion. Now don't say the charge on the metal ion, the IB get their knickers in a twist over that and they won't give you the point. The charge on the metal ion in the first one is 2+, but the oxidation state is +2. Subtle difference, +2 for the oxidation state. So the lower the oxidation state, the smaller the split, because the less the interaction with the ligands. So the iron +2 oxidation state has a small split, red light's absorbed, electron is promoted, and the complex is green, because when your eye sees orange, yellow, green, blue, indigo, violet, it perceives green. For the second one, the oxidation state is +3, bigger split, bigger oxidation number, so it has to absorb a higher energy. Actually, it absorbs violet, and so it appears yellow. Okay, some questions. Which complex would have the highest energy gap, absorb the highest... Oh, I just got to switch to the Iron Maiden. It's my favourite solo. Just give me a second. Chemistry in a second. Fantastic. Okay, so that's a trick. Those are all the same. Those are all the same question. So you have to be able to spot the 3 different sorts of examples. The first one is the oxidation state makes a difference. So the chromium 3+ has the bigger split. The second one, they're isoelectronic to each other. So more protons, more interaction with the ligands, bigger split. So it's vanadium. And the final one, you have to look at the spectrochemical series. The one further to the right has a bigger split. So the ammonia-based one. Smashing.
Okay, so from the video, you would have seen that the many complex ions are coloured because of the energy differences between the d orbitals, which of course is related to the ligands, related to the size of the cation in the center, and also related to the actual nature of that cation. So the colour absorbed can be determined by taking the colour transmitted, what we actually see, and finding the opposite wavelength on the colour wheel from the data booklet. Okay, so larger splits require high energy transitions, so that's why they have they absorb in the violet range, so they tend to be more yellow, and smaller splits tend to be lower energy, so looking at the reds, they tend to be greeny blue. Some real world examples, okay, co-canundum, aluminium oxide basically is colourless, whereas ruby, which has 1% chromium 3+ in it, is red. Okay, so if you look at the reasoning behind this, if you look at the absorption spectra of ruby, it has 2 absorption maxima, one around the blue, okay, around 450 nanometers, one around the kind of reddy orange, okay, around 570, 580, and that corresponds to the complementary colors of blue and a nice red, and it's that combination of colors which gives ruby its nice ruby red color. Okay, and beryllium silicate of some nature is colorless, well, at least clear, and emerald is a nice emerald green with chromium 3+ in there in the crystal lattice. So again, looking at the absorption spectra, it absorbs in the region of 450-ish and 600. Okay, so that's going to correspond, not quite 600, it's more like 500, which is going to correspond to emission spectra of in the green, okay, and a little bit in the blue, not so much, but in the green. Okay, so that's why you see it as green, because it absorbs in the 500 to 500 nanometer maxima and or 600 nanometer maxima and 400 nanometer maxima, and it then emits in the region of 430 nanometers, which is corresponding to green. Okay, so that's the reason why you see emerald as being green. Okay, you can see therefore the effect of strength of ligand. Okay, so this guy here, the water dichloro complex, okay, it is transmitted as green because this causes a reasonably small split. So red light, low energy, allows that transition to occur. But as you go on, by now adding, I guess, stronger ligands, like now you've substituted with 2 more waters, that's going to require a larger split. So you're absorbing in the green region and therefore transmitting in the kind of red burgundy kind of region, high energy. And as you increase the strength of a ligand, it requires blue and purple. You're going to get the corresponding high energy light being, well, complementary color being emitted. Okay, so that's the example of how changing the ligand can affect the split and therefore affect the color of the, not only the color being absorbed, because you need these high energy transitions, but also the color being emitted.